¿Estáis silenciosos o es que no oigo yo? Luca, ¿me oyes?
No, sí, te oímos.
Ok.
Entonces, vamos a empezar ahora mismo.
Vale, no la estaba chequeando. Vale, gracias.
Nada. So Wolfgang, if you're ready, we can start. I present you.
Sounds good.
So welcome everybody to this Monday talk. Today we have the pleasure to have with us Wolfgang Altmannshofer. He's a great expert of flavor physics, especially in this case decays, and he's going to speak about the state of the situation in decays anomalies. So please, Wolfgang.
Thanks, Luca. Thanks for the invitation, for the introduction. So I'm very happy to be here virtually and to give this talk about decay anomalies. It's several years now that there are these anomalies in decays that are observed primarily by the LHCb collaboration. And what I want to do in this talk is to give an overview on the one hand of the experimental situation. There have been recent updates a couple of months ago of some of the measurements that show discrepancies. And I also will interpret then these measurements in the context of new physics and discuss how new physics or how these results might point to new physics, which type of new physics. And I will also say a bit about the future, how with more data one might be able to sort out what's going on here. Now, before going into the details of the decay anomalies, let me just spend a few minutes in setting the stage and talk a bit about flavor physics in general. So what is shown here on this slide is the Lagrangian of the standard model in a very condensed way. And then the first line here, we have the Higgs potential. The second line, the kinetic terms for the quarks and leptons, for the Higgs boson and for the gauge bosons. And then in the third line here, these are the Yukawa couplings of the quarks and leptons with the Higgs boson. And it's those Yukawa couplings which introduce the concept of flavor to the standard model. So the first two lines here, the Higgs potential and the kinetic terms, they are invariant under flavor rotations. They don't know anything about flavor, but it's the coupling of the Higgs to the quarks and leptons which introduce the concept of flavor, which distinguish the different flavors of quarks and leptons, providing the different masses to the different flavors of quarks and leptons. And now, if you look at these various terms in the standard model, many of them are related to all kinds of problems and unsolved questions. In the case of these Yukawa couplings, it is the standard model flavor puzzle which is related to them, which is the question of why the masses and flavor mixing angles that come out from those Yukawa couplings show such a hierarchical structure. So we know that when we look at the masses of the quarks and leptons, they span many orders of magnitude, from the heaviest quark, the top quark, to the lightest charged fermion, the electron. It's almost 6 orders of magnitude between their masses. And these Yukawa couplings in the standard model, they can accommodate that, but there's no explanation of why such a hierarchy should be present. Similarly, also, if you look at the mixing angles among the quarks, the CKM quark mixing matrix, the entries of the CKM matrix, again, they show a very hierarchical pattern with some entries being much smaller than others, some off-diagonal entries being as small as few times 10 to minus 3, while others are very close to 1. So again, there's no explanation in the context of the standard model why such hierarchies should exist, and that's typically referred to as the standard model flavor puzzle. If we regard the standard model as an effective theory, only valid up to some new physics scale lambda, we can sort of extend this Lagrangian and add in higher dimensional operators. At dimension 5, we get neutrino masses, and then at dimension 6, we get a large set of additional effective interactions, which can in principle also violate flavor, which can lead to additional flavor mixing between both quarks and also among leptons. And then one can use low energy measurements of flavor violating processes to probe these types of dimension 6 interactions, these effective interactions, and try to understand if there's any new physics that indirectly shows up in this way. Yeah, so just to summarize the sort of the role of flavor physics, or the goal of flavor physics in that picture is twofold. On the one hand, there's this standard model flavor puzzle, so the question of what is the origin of the hierarchies in the standard model, sources of flavor violation, what is the origin of hierarchies in the quark and lepton masses and the quark mixing angles. And then the second question is, are there new sources of flavor violation beyond the standard model? Is there anything out there beyond the standard model that violates flavor and that can be tested with low energy flavor changing measurements? And then we can let me just give also a very quick review of how that actually works, how one can indirectly discover new physics that potentially lives at very high scales with low energy flavor changing processes. And the classic example here is to look back at beta decay, the decay of a neutron to a proton, electron, and an electron antineutrino, and all that one can describe by an effective low energy Lagrangian. One can introduce a 4-Fermi contact interaction between a neutron, a proton, the electron, and the electron antineutrino. And the corresponding interaction strengths then is parametrized, or is given by the Fermi constant, because it's an effective 4-Fermi contact interaction. This Fermi constant has a mass dimension of -2, and therefore it defines an energy scale, and that energy scale corresponds to something like 250 GeV. Of course, in the context of the standard model, we know that the Fermi constant actually arises from the exchange of a virtual weak gauge boson. So what is actually happening is we have a down quark going to an up quark through the emission of a virtual W boson, which then goes into an electron and the electron antineutrino. And then we can compute in the context of the standard model what the value of the Fermi constant is, and it is related to the coupling of the W boson and the W boson mass. And in fact, the W boson mass that we know is not too far away from this scale that we could just infer from measurements of nuclear beta decay itself. So W boson mass is around 80 GeV, which is a factor of 3 or so lighter than this intrinsic scale of this 4-Fermi contact interaction, which is around 250 GeV. So long before the W boson was actually discovered, it was possible to understand or to infer that something around that scale, around the mass of, let's say, hundreds of GeV should happen. And in fact, the W boson was discovered, and many years later at around 80 GeV, giving this, in some sense, this new physics explanation of where this 4-Fermi contact interaction came from. And now we can do something similar with flavor changing processes. If you look at the standard model, here this example of the decay of a B quark, and flavor changing currents, flavor changing charged currents, they arise at the tree level in the standard model. So again, we have an exchange of a W boson, which can lead to the decay of a B quark into a charm quark, and then, for example, a lepton and a antineutrino. And that transition here from a B quark to the charm quark again is given by this exchange of a W boson. So we get effectively the Fermi constant, but the corresponding amplitude now is suppressed by a CKM matrix element, in this case as a CKM matrix element VCB, which turned out to be a numerically small number. Those are corresponding 4-Fermi contact interaction here. This G is given by the Fermi constant times this CKM matrix element. We can also look at so-called rare decays. These are decays of a B quark, either to a strange quark or to a down quark. So we are staying within the same class of fermions, but we are changing the flavor. And such flavor changing neutral currents, they arise only at the loop level, so they don't exist at the tree level. it's a Chim mechanism that forbids this type of transition at tree level, but one can always do the detour through the up sector at the loop level. So going from a B quark to a top quark, and then the top quark going to the strange quark. So that is something that can happen at the loop level. That is top W loop here. And then, for example, one can attach a photon in this diagram down here and get a muon antimuon. So in the end, one has a transition from a B quark to a strange quark and a muon and an antimuon, and we can estimate what the corresponding effective four-fermion contact interaction is, and that will be given by a loop factor, again the Fermi constant, and there will be some factors related to the mass of the quark in the loop, and then again a CKM suppression, this time CKM matrix element VTB and VTS that are showing up in this amplitude. So one can describe these types of transitions, these types of B decays in terms of effective interactions, dimension 6 operators, and in the context of the standard model, one can actually compute what those corresponding amplitudes or these corresponding coupling constants, these effective coupling constants are. And then the basic idea is very simple. One tries to measure these types of transitions very precisely. One calculates these transitions in the standard model as precisely as possible. And then on top of that, one would add possible new physics contributions. New physics contributions parameterized in terms of a four-fermion contact interaction, and then one would just parameterize it in terms of some new physics coupling divided by a new physics scale squared. And then by comparing the measurements of those types of conditions with the standard model predictions, one can then get information about possible new physics contributions. So if we, on the one hand, if we would get agreement between the standard model prediction and the measurement, we can put constraints on possible new physics contributions. On the other hand, if there's a discrepancy between the measurement and the standard model prediction, one could attribute that to a possible new physics effect, and then even infer what a possible scale of new physics is that could be causing this discrepancy. So anomalies in flavor observables, the discrepancy between standard model prediction and the measurements, they could establish a new scale in particle physics, which could be very high, and then that scale then would be a possible goal to explore with future colliders. In fact, if one assumes now that one has such a rare B decay, and one observes a order 1 discrepancy between the measurement and the standard model prediction, if one plugs in numbers into this expression here, one finds that the new physics scale is of the order of tens of TeV. So it's actually potentially outside the reach of the LHC, but it could be within the reach of future colliders. On the experimental side, we have now the LHC, which is in fact a B factory. It produces a lot of B quarks. What is shown in this plot here is the integrated luminosity that the LHCb experiment has been collecting over almost the last decade or so. And the data that they have collected corresponds to roughly 10 to the 12 B quarks. So they have something like 10 to the 12 B quarks to work with. And therefore, they have access to many rare B decays, rare processes that are these loop suppressed processes. Many of those processes have been measured for the first time at LHCb, or some of them have been measured with unprecedented precision at LHCb, and this allowed us to make then tests with respect to standard model predictions and to see if the predictions that we have in the standard model do agree with those very precise measurements that were coming out over the last years. And what happened is that several of those measurements show discrepancies with standard model predictions, and they are briefly summarized in this plot here, and I will discuss them in much more detail throughout this talk. I just want to give you a brief overview of those various anomalies. And let me first of all distinguish between charge current decays and neutral current decay anomalies. There are these these blue observables here called RD and RD star, they are related to this B2 charm L-nu transitions that I had in one of the earlier slides, these tree-level decays of a B quark to a charm quark, a lepton, and a neutrino. And what RD and RD star are, those are ratios of branching ratios with different leptons in the final state. In particular, these are ratios of branching ratios with taus in the final state and with muons and electrons in the final state. And those ratios of branching ratios, they don't agree well with standard model predictions. They are off by 2 to 3 sigma. Similarly, for this flavor change neutral current decays, for this rare decays, for the B to S LL transitions, we have these ratios RK and RK star. Again, these are ratios of branching ratios with muons and electrons in the final state. Also, they show discrepancies. And then there are a bunch of other observables. There are individual branching ratios of B decays. We have the branching ratio of a B sub S meson into 2 muons, branching ratios of a B meson into a kaon and 2 muons, B to K star, 2 muons, B sub S to phi, and 2 muons. All those branching ratios, they disagree with standard model predictions. And there are also measurements of angular distributions in B to K star and mu. The decay products, the K star and the muon and the antimuon. One looks at the angular distribution of those decay products that can also be predicted in the standard model, and also those angular distributions, they show discrepancies with standard model predictions and the measurements. So there's a bunch of different things that are going on here. What is shown in this plot here is not only the significance on the x-axis, but also what is written here as the relevance of hadronic effects. So in some sense, this is how clean. This is a measure of how clean the standard model prediction actually is. So the higher you are on that axis, the cleaner the standard model prediction is, and the more you should trust the significance that is on the x-axis. So in particular, these ratios RK and RK star, those are considered to be theoretically very clean. There's very little uncertainty on the standard model prediction. And therefore, these discrepancies are regarded to be very clean hints for new physics. And if the significance of those increases, then this should be a clear hint that something is happening here in terms of new physics in these rare B decays. That was a very quick overview. Let's now go through these various observables, these various decay modes in more detail. So let's discuss this rare. And what I will do is I will focus on the rare B decay anomalies, so the red ones here, and I will not discuss the charge current decays in this talk. Let's start with arguably the simplest version of these rare B decays. That is a decay of a B sub S into mu plus mu minus. So the B sub S is a bound state of an anti-B quark and a strange quark, and you will decay into a muon and an antimuon at the quark level. That is this transition from B to S, mu plus mu minus. And because it's a two-body decay, the kinematics there is fixed. So what one expects to see experimentally is a dimuon resonance at the mass of the B sub S meson, and that is exactly what is done experimentally. One looks for a dimuon resonance at the mass of the B sub S meson, and shown here is a plot from LHCb, the dimuon invariant mass, and then one sees a nice peak at the mass of the B sub S meson, and by measuring the height of that peak, one can translate that into a branching ratio of that decay mode, and combining not only the LHCb results, the LHCb measurement, but also results from CMS and Atlas, one finds as a world average this result here around 3 times 10 to minus 9 as branching ratio. And the standard model prediction for that branching ratio is a bit higher, so 3.6, 3.7 times 10 to minus 9. It's not a huge discrepancy, but it's sort of a 2 sigma-ish tension between standard model and experiment. By itself, that wouldn't be very, very exciting, but as you will see, there's a trend here that it's not only this B sub S to mu plus mu minus branching ratio, but many other branching ratios that show similar behavior. So the branching ratio here that is predicted in the standard model is slightly higher than the one that is actually measured. So let's look at a slightly more complicated decay now. It's in our semi-leptonic version, a p meson going into a kaon, a muon and an antimuon. At the quark level, it's the same thing. We have a p quark going to a strange quark, a muon and antimuon, and now we have an up quark or an anti-up quark as a spectator. And not only this B2K mu, there's a B2K star mu. It's the same quark level transition. We have a B sub S to phi mu, again, the same quark level transition. We just flipped what the spectator quark is in those cases. And what is shown here in those three plots are the measured differential branching ratio as a function of Q squared, where Q squared is the dimuon invariant mass. Now we have a three-body decay, so the dimuon invariant mass is not anymore the mass of the B quark. Sorry, it's the B meson, but it's now a kinematic variable that can range from basically 4 times the muon mass squared up to a kinematic endpoint that is given by the mass of the B meson and the other meson in the final state. And what is shown here are the various measurements. These black crosses here in case of B2K mu, here down here is a B sub S to phi mu, and here we have a B2K star mu. And this is compared to the standard model predictions, which are, well, these various shaded regions here. In case of B2K mu, it is this very broad greenish area down for B sub S to phi mu. We have different types of standard model predictions based on different hadronic input. One needs form factors for the B sub S to phi transition, and for the B2K transition, and for the B2K star transition. And depending on what one exactly does with these form factors, one gets slightly different standard model predictions. But one can see a very clear trend here that all those measured branching ratios, that they are below the standard model predictions. Now one can argue of how well one actually knows the standard model prediction. As I said, one needs form factors that describe those various meson transitions, and it's beyond form factors. There are also so-called non-factorizable effects, other non-perturbative effects that need to be taken into account. One needs to some extent model those effects. One needs models of QCD to understand how big those effects are. And so it's not easy to assign a reliable estimate of how big the uncertainty on the series side really should be. And that is reflected here, for example, in this plot of B sub S to phi mu, and the different widths of those standard model predictions here. So the width of those boxes here, those comes from just making different assumptions about how which information one uses to make the standard model prediction, and which methods one is using to come up with the uncertainty on the standard model prediction. And one can argue that maybe these uncertainties are all underestimated and they should be even bigger. In that case, the significance of this discrepancy is not very large, but definitely seems to be a trend that, as in the case of B sub S to mu mu, also the semi-leptonic decays, they seem to be low if we look at the measurement compared to the standard model prediction. Then let's also look at this angular distribution that I had mentioned before. So here we are looking at the B2K star mu mu decay. So we have a P meson going to an excited kaon and a muon antimuon pair. And this excited kaon, this K star, that decays further into a kaon and a pion. So one actually has a 4-body final state. And one can look at the angular distribution of those 4 particles in the final state. And just here, what is shown in this plot here is an actual event display of how this decay looks like in the detector, in the LHCb detector. If in the middle there's a primary vertex where the proton-proton collisions take place, and one creates a P meson, which then flies a certain direction. And then there's a secondary vertex here where the decay of the B meson occurs. And here one sees the two muons coming out, and then there's also a kaon and a pion, and they all four come from this same secondary vertex. That's a clear signature of this B to K star mu mu decay. And then there's these four particles in the final state, so one can look now at how those four particles are distributed in phase space. What is the angular distribution of those four particles? And one observable that has been measured is called P5 prime. You can think of it as a moment of this angular distribution, and measurements of this P5 prime have been done already many years ago. Here, what are shown here in this plot here are measurements from 2015 by LHCb, also compared to other measurements from Atlas, Bell, and CMS. And measurements are still sort of a bit all over the place, but the most precise ones, the LHCb measurements, the black ones here, they show quite a bit of discrepancy between measurements and the standard model predictions. These purple and orange boxes here. Something like a 2.5 sigma discrepancy in a couple of Q-square bins. Again, one can ask the question of how precisely do we actually know the standard model prediction? Again, there will be now this P5 prime is constructed such that these angular distributions are sort of cleaner than branching ratios themselves, because one is not sensitive anymore to overall normalizations of form factors or things like that, but one is still sensitive to all kinds of hadronic effects, which are hard to estimate. So again, one can ask the question of maybe there is some additional uncertainties which are underestimated here. Maybe this standard model prediction should have bigger uncertainties. These boxes should be maybe bigger, and then it wouldn't be a 2.5 sigma discrepancy, but maybe only a 2 or 1.5 sigma discrepancy, depending on how generous one is with assigning uncertainties to the standard model predictions. But in any case, also here there seems to be something going on, at least at face value. The measurements don't agree very well with the standard model predictions. Last year there have been updates of this P5 prime measurement. This is the situation as of roughly a year ago. Here see again P5 prime as a function of Q squared with the standard model predictions, and the measurements which do show the same discrepancy as in the old data. So including the results from including data from 2016, this discrepancy persists. There are also newer measurements with a slightly different set of decays. So instead of looking at neutral B mesons decaying into neutral K stars with mu plus or minus, we can also look at charged B mesons going to charged K stars with mu plus or minus. So this is experimentally a bit more challenging. And the uncertainties on the experimental side are much larger now here. But again, one sees the same trend in these two Q square bins. This P5 prime measurement is quite a bit above the standard model prediction. So there one sees consistency in across different types of B decays. The final class of observables are these lepton flavor universality ratios, these RK and RK star ratios that I had mentioned before. Here's how they are defined. It's a branching ratio of a B going into a kaon and 2 muons divided by the branching ratio of a B going to a kaon and 2 electrons. So this RK, and then RK star, the same as the excited kaon. And here now the standard model prediction is very clean. The standard model predicts that this ratio should be 1 with very high precision. And what is shown here are the measurements. Here's the situation as of a year ago or so. So we have a RK and an RK star measured in a few Q square bins, which are indicated here by these values in parentheses. So it's a Q square bin from 1 to 6 GeV squared for RK, and then two Q square bins for RK star. And those measurements they are smaller than 1, and they deviate from the standard model prediction by around 2 to 2.5 sigma. And that's also shown in these plots here. Now, very recently, something like 2 months ago, there have been updates of RK. So this value of RK has been updated with the full run 2 data set from LHCb, and the central value actually stayed exactly where it was before, but the uncertainties shrank as one would expect by adding more data to it, and now this discrepancy between the standard model prediction and measurement is above 3 sigma. It's 3.1 sigma with the latest update from LHCb. So they claim now they have evidence for lepton flavor universality violation in those rare BDK, B2K, LL. Now I said that in the standard model, these R ratios, RK and RK star, they are known with very high precision. So how well do we actually know those ratios in the standard model? And so let's just go through that in a bit more detail. So at leading order, RK and RK stars, they should be 1. It's just a ratio of those branching ratios, the actual interactions that are behind those B2S LL transitions. They are lepton flavor universal. The weak interactions don't distinguish between muons and electrons. So that should give a value of 1. But there are phase-based effects in principle. So because the muon is heavier than the electron, the phase space of those decays is slightly different, and that should give an effect of the order of the muon mass squared divided by q squared. So where q squared again is the invariant mass of the 2 leptons in the decay. So if one is at low q squared, there will be some small effect due to the different masses of muons and electrons. But because in general, because B mesons are much heavier than electrons and muons, q squared on average is much bigger than the muon or electron mass, and therefore these effects are very small. In this q square bin from 1 to 6 GeV squared, for example, the effect is at the per mil level. And now, even though the individual branching ratios are not known very well, we have these large hadronic effects, large hadronic corrections in principle. In these RK and RK star ratios, those effects they cancel almost exactly, because again they are the same for muons and electrons. QCD effects they do not care about the flavor of the lepton in the final state, so they do cancel out, but they cancel out up to those phase-based effects where they don't fully cancel. So these phase-based effects, in principle, we don't know them very well. There will be large uncertainties, but we know that overall they are tiny. So therefore, these hadronic corrections, they don't really play a role in the prediction for RK and RK star. What does play a role potentially are QED corrections. So muons and electrons, they radiate photons very differently. There can be, in principle, large logarithms that one gets from soft and collinear photon emission. And those things need to be taken into account. They need to be understood in order to make standard model predictions for RK and RK star. And that has been done. So people looked into that in quite some detail. And what one finds is that given how the experiment is actually done, how electrons and muons are measured and reconstructed, these QED corrections are actually well under control. They are at a few percent level, and they are actually taken into account in the experimental analysis by simulating this photon emission. And in the end, one finds that the uncertainty on this RK and RK star values in the standard model are around 1% or so. So RK and RK star are 1 with high precision, with a percent level precision. If one goes to this Q bin that I had shown also before, which is very low, this RK star measurement at the low Q square bin, there one sees this phase-based effect. So there one has not a prediction of 1, but around 0.9 with a slightly larger uncertainty. What I should also mention is that one expects potentially larger QED effects at a differential level. So if one doesn't measure ratios of branching ratios, but if one tries to understand ratios of angular observables or differences of angular observables in electrons and muons, there one might have slightly larger QED corrections and larger uncertainties due to those QED effects. But for the ratios of branching ratios, this seems to be very well under control. Okay, so what could all of that actually mean? We have these various anomalies in the various types of observables. So what could it be? There could be experimental issues, which those various things that I discussed. I'm not an experimentalist, so I don't feel qualified to speculate what should be going wrong. But that is an option, I guess. So it could be statistical fluctuations. Each single one of them is at the level of, let's say, 2 to 3, maybe a bit more than 3 sigma. So each single one of them, I guess, by itself could be a statistical fluctuation. And for some reason, they seem to be piling up in this rare PD case, but I guess we can't exclude that at the moment. Parametric uncertainties. What I mean with that are things like input from CKM matrix elements or overall normalization of form factors and things like that. So there, that could be a reason that some of those things are off from the standard model prediction. It could be the reasons for the Phasebased to be plus minus rate, which depends on the CK element VCB. There might be some underestimated uncertainty here. Also, the Semielectronic rates, the branch ratio of B2K mu, Phasebased to phi mu, B2K star mu, those also could be explained with parametric uncertainties. Angular observables, this P5 prime and this lepton Flavor and Salty ratios, RK and RK star, they are independent of these types of parametric dependencies, right? These types of observables are constructed such that they are independent of CKM matrix elements or overall form factor normalizations. So those observables are clean in that sense and couldn't be explained by parametric uncertainties. I had mentioned these other hadronic effects, non-factorizable hadronic effects that need to be taken into account and need to be estimated. And they could be behind the discrepancies in the semielectronic rates and in the angular observables, but they can't explain the reduced Phasebased to plus minus rate, and they can't also explain these lepton flavor universality ratios. And finally, there's the option that it might be new physics, and new physics in principle should be able to explain all those things as well. So we don't know what the actual answer is. It could be a combination, of course, of many of those things, but the new physics option, of course, is the most exciting, and that is the one that I will discuss now in a bit more detail in the coming minutes. What one does in a new physics analysis is to parameterize all possible new physics effects that could contribute to these types of P2S LL transitions in terms of an effective Hamiltonian. So one includes all the dimension 6 operators, all the effective dimension 6 interactions that could contribute, and then parameterizes the new physics effect in terms of Wilson coefficients of those operators. And here's this is very well known. This is very one can do that in a very systematic way. The most important operators, the most important effective interactions are listed here. One has so-called magnetic dipole operators, interactions between a B quark and a strange quark and a photon. The corresponding Wilson coefficients are referred to as C7 and C7 prime, depending if it's a left-handed or right-handed B quark that sits inside this interaction. And then one has semielectronic operators. Those are now either vector currents or axial vector currents for the muons, which are coupled to currents of left-handed or right-handed currents for the B to S transition. And then the corresponding Wilson coefficients here are called C9 and C9 prime and C10 and C10 prime. And then there are scalar operators where one has scalar currents for the muons and for the B to S transition. And these are CS and CS prime. And then one can switch on those additional effective interactions and try to understand if any of those interactions will lead to better agreement between predictions, theory predictions, and the measurements. Now that turns out to be rather involved, because whenever one switches on one of those effective interactions, it will simultaneously modify a number of different things. So for example, if one includes new physics in form of these dipole operators, this Wilson coefficient C7 and C7 prime, and will get simultaneously new physics effects in a large set of decay modes. We will get effects in radiative decays, B2 S gamma decays, or exclusive B2K star gamma decays, also B sub S to phi gamma decays, in the semielectronic decays of B to K and K star, mu plus or minus B sub S to phi, mu plus or minus lambda B to lambda, mu plus or minus baryonic decays. And the only thing that is wouldn't be affected by these type of operators is the B sub S to mu plus or minus decay. Similarly, for these semielectronic operators, C9, C9 prime, C10, C10 prime, a large set of observables will be, large set of decay modes will be affected simultaneously. And then within each decay mode, there will be several observables like branching ratios and angular distributions, which get modified in a particular characteristic way that depends on those different types of operators that one is switching on. So what one needs to do is actually to do a global fit, because many processes, many observables within those processes are modified simultaneously. So one needs to take all of that into account to understand if there's any type of new physics that could lead to an improved agreement between prediction and measurement. And I have been doing things like that almost a decade now. So we started doing these type of things long before there actually were these B anomalies. The original idea was simply to constrain possible new physics that could show up in this rarity case. But once those B anomalies showed up, then it became an exercise trying to figure out which type of new physics is actually preferred by those measurements, which type of new physics could explain these discrepancies. And yeah, there have been now many groups who are doing these types of studies. Here's just a short list of the most recent papers that came out in this context. And what I'll be showing here in the next few slides are results from my paper, which came out a couple of months ago. Okay, so what is shown here is now a table where one switches on one operator at a time, one new physics operator at a time, and one puts new physics into the B to S EE transition, which is the one which would lead to modified RK and RK star values. And depending on which Wilson coefficient, which operator one switches on, what one is shown here is the best fit value for that coefficient and the pull value with respect to the standard model. So pull here means the square root of the delta chi-squared between the standard model point where this Wilson coefficient is 0 and the best fit point. And what we can see here is that if one looks at the lepton flavor universality ratios and the B sub S to plus or minus decay, if one includes that experimental information, one finds that some of those new physics interactions, they can lead to something like a 4 sigma improvement with respect to the standard model. If one includes all the rare B decay data, so not only RK and RK star and B sub S plus or minus, but also all the other branching ratios and the angular distributions, one doesn't gain anything here because one puts new physics in the electrons, and all these other rare decay measurements, they are done with the muons. So here nothing really changes. And another thing to keep in mind here, just for comparison, what do these values mean? The normalization here is such that in the standard model, C9 and C10 are around 4 and minus 4. So one has here 15 or 20% new physics effects that could lead to this 4 sigma improvement. Now looking to the new physics in muons, now we switch on new physics in the operators which contain muons. Situation, if one only looks into RK and RK star and B sub S plus minus, is similar. 4, a bit more than 4 sigma pulls for each of those, for some of those interactions. But now, if one includes also the data for all the other rare B decays. The branching ratios and the angular distributions, one in some cases finds close to 6 sigma pulls with respect to the standard model. So there's a very high preference for a non-standard muonic C9 or C10. And if you trust the theory errors that go into our theory predictions, then one gets these pulls of around close to 6 sigma. If you don't trust the theory errors, and you probably shouldn't, because there are all kinds of issues, and it's not always clear how one should estimate those uncertainties. So if you don't trust them, you can still trust those values here in this first column, which tell you that these pulls are still above 4 sigma. Now, in some sense, it's hard to interpret those pull values in terms of an actual significance of the overall effect. In some sense, those pull values here are sort of a local significance in some sense. And actually, there have been studies trying to understand what is the global significance of all those anomalies. If you take together the fact that we have these various measurements which show discrepancies, but on the other hand, there's also many measurements which don't show discrepancies. Some of those angular distributions, other than P5 prime, for example, they show good agreement with standard model predictions. So I can sort of come up with a global significance which takes into account a look elsewhere effect. And that has been done recently, and they conclude that the global significance of all those discrepancies is around 3.9 sigma. In any case, another exercise one can do is to show the results also in the plane of 2 Wilson coefficients, and one switches on 2 new physics operators simultaneously, and one can see what now the best fit ranges are in those cases. What is shown here is C9 for the muons versus C10 for the muons, and here's again the definition of those operators. C9 corresponds to a vector current for the muons and a left-handed B to S transition, and C10 is an axial vector current for the muons and a left-handed B to S transition. And if one looks at the lepton flavor universality ratios, RK and RK star, they overlap here in this blue region. There's some preference for a positive C10, but there's large degeneracy, so the very large region of where RK and RK star can be explained in the context of these 2 effective interactions. If one switches on, or if one takes into account also all the other information that we have, the B-Sebastian Crossvenous branching ratio gives this yellow band here. The B to S mu observers, branching ratios, and angle observers, they gives this orange ellipse here. And then the red region, that is then the global fit, taking into account everything simultaneously. And then the best fit point in that case is somewhere here with a C9 of around -0.6 and a C10 of plus 0.25. And overall, there's a pretty good agreement between those different classes of observers. So one has nice, at least at the 2 sigma level, one has a very good overlap between those different regions. I can, in principle, go ahead and predict other observers. So given this best fit range that we find, one can make predictions for, let's say, other lepton flavor universality ratios. What is shown here is a list of those ratios: RK, RK star, R phi in different Q-square bins. And in blue are the predictions of this best fit in the physics model, this best fit in the physics scenario. And in red are the standard model predictions. And then in black, the current measurements. It's the most precise measured value of this RK. It's a recent update from 2 months ago. That is sort of mainly driving this new physics scenario. And then there's the RK star measurements, which are quite a bit low. So it would be interesting to see what happens with RK star in the future when new updated results are coming out. And it also would be nice to see all those other lepton flavor universality ratios to see if they also line up with those new physics predictions. the beginning, I've talked about new physics scales. So what one can do is that the next step is to translate these best fit values for the Wilson coefficients into scales of new physics. And that depends on what one assumes was a coupling that new physics has. If one takes this generic tree level scenario, one says the coupling is order 1, so new physics coupling is order 1, then one can directly translate these values for C9 or C10 into a new physics scale. And that scale is typically around 35 TeV or so. If one makes other assumptions about Wilson coefficients or about the new physics couplings, one gets different values. If one puts in CKM suppression, or if one puts in a loop suppression, or both CKM and loop suppression, one gets values that range from several TeV down to several hundred GeV. And if one puts a very large coupling, for example, of 4 pi, one would get a new physics scale of up to 120 TeV or so. So there's a broad range of new physics scale that in principle could be behind those types of discrepancies. So depending on which assumption one makes about how this new physics is coupled, one gets new physics scales between a few hundred GeV and up to maybe 100 TeV or so. In terms of an explicit model, my favorite model is a C prime model that is based on gauging the difference of muon number and tau number, and mu minus L tau. That is a anomaly-free symmetry in the standard model without neutrino masses. So one can gauge it consistently, and then one has to introduce some way of coupling this C prime to quarks. One can do that by introducing some heavy vector-like fermions that couple to the Z prime and then mix with the standard model quarks. So here's a simple realization of a contribution to the B to S mu transition mediated by such a Z prime gauge boson, which has a gauge coupling to the muons that gives a vector current to the muons. And then one has this heavy vector-like quarks, which probably have a mass of several TeV or so, and that mix into the B quark and the strange quark, giving this effective B to S mu transition. And actually, we wrote down that model quite some time ago, already before RK and RK star measurements came out. So we actually have a prediction in that paper that lepton flavor universality should be violated, and actually that's exactly what was then observed by LHCb when the RK and RK star measurements came out. One can ask, what is the viable parameter space of that C prime gauge boson? In principle, the C prime gauge boson can have masses that cover a very broad range. What is shown here in this plot is the mass of the C prime versus the corresponding gauge coupling. And in this white region up here, the C prime can explain those B anomalies. It can have masses between around 10 GeV or so up to several TeV. The corresponding gauge coupling then is between 10 to minus 3 and 1 or so. And it is constrained mainly by B sub S mixing. So if the C prime exists and has this flavor changing B to S coupling, it will also contribute to B sub S mixing. And that can exclude this parameter region here. And then up here, it is constrained by many different types of measurements, lab measurements of Z boson couplings, neutrino scattering experiments, direct searches at the LHC, so they all constrain that parameter space up here. But there's this parameter region left over, which can explain the B anomalies in the context of this Z prime model. Interestingly, the same C prime can also explain the G-2 of the muon, but it can only do so if it's very, very light, only if it's around 100 MeV or so. So for a very, very light C prime, one could, this C prime could explain the muon G-2, the anomaly in the anomalous magnetic moment of the muon. But that parameter region is very distinct from this parameter region where one can explain the B anomalies. So one cannot do both things simultaneously in the context of that model. One can either explain the B anomalies or G-2, but not both of them at the same time. I think I'm running a bit out of time. Let me speed up a bit. There are other predictions that this model, the C prime model, makes. The most important one, which is, however, difficult to test experimentally, is that the coupling of the C prime to muons and to taus has opposite sign. So the C prime model predicts that there should be opposite effects in the mu plus mu minus and the tau plus tau minus final states. The mu plus mu minus final states are measured by LHCb. The tau plus tau minus final states are much more difficult to access experimentally. But one would expect in the context of this model that all the decays into taus are enhanced by, let's say, 20–25% or so compared to standard model predictions. That would be the smoking gun signature of this model, but it's very, very hard to test experimentally. Here are a set of other predictions. This model predicts that there's no lepton flavor violation of the C prime. So even though there's violation of lepton flavor universality, there's no lepton flavor violation directly. So there's things like Phasebased to tau mu or B to K star tau mu. Those things are absent in this model as they are absent in the standard model. But that's in contrast to many other new physics models that people have proposed to explain the B anomalies. Similarly, this C prime model, the mu-minus tau model, it predicts no new physics effects in Phasebased mu plus mu minus. So Phasebased mu plus mu minus in that model remains standard model-like. So I've showed at the beginning there's this slight 2 sigma tension between the measurement and the standard model prediction. So if that grows, that is one way to exclude this mu minus tau model. And then there are also predictions for decays with neutrinos in the final state because of SU2 left symmetry. Effects in charged leptons are related in many cases to effects in neutrino decay modes. And in this mu minus tau model, one finds that these neutrino modes are standard model-like to a good approximation. One suppresses the decay into muon neutrinos and one enhances the decay into tau neutrinos. But because in these types of decays, one cannot measure the flavor of the neutrinos, the overall effect cancels out, and one gets B2K nu nu and B2K star nu decays, which are standard model-like. And again, that is in contrast to many other models that are that have been proposed to explain the B anomalies. One can extend also this model to see how robust these predictions are, but I think I'm skipping that because I'm running out of time. Just want to show as the last slide possible future prospects for measuring these lepton flavor universality ratios. So that will be very interesting in the future, trying to understand if RK and RK star really do show these discrepancies with standard model predictions, or if these are maybe statistical fluctuations. It doesn't look like, based on the recent experimental updates, which show the same central value and increased precision. But it will be very, very interesting to monitor what's happening here with more data that LHC will be collecting, and also BEL2, the BEL2 experiment, which is now starting to collect data. It will be very interesting in the coming years to see if those anomalies in RK and RK star remain, and if they can be confirmed also with other decay modes, things like R phi or R proton kaon. Things like that will be very, very important to observe. And one can even look at things like lepton flavor universality in angular distributions, measuring, for example, this P5 prime observable, not only for muons, but also for electrons, and then looking if there's any significant difference between those. That also will be something that will be happening with more data. So in the next few or several years, there will be a lot of activity in this area. Okay, here's my summary. I've discussed that there are in the rare B decay data, there are various discrepancies. They continue to to be there with the latest updates. One has discrepancies both in branching ratios and also in angle observers. These branching ratio and angle observer discrepancies, they could be explained by new physics, but also with underestimated hadronic effects. But this evidence for lepton flavor universality violation that we have, that is on the one hand nicely compatible with the other anomalies, but also it is theoretically very clean. So therefore, if the significance of lepton flavor universality violation continues to grow with more statistics, then this would be a very clear indication for new physics. Maybe it is a gauge universal tau gauge boson, or maybe something else. And hopefully with more data, we will be able to figure out what's going on. All right, thank you.
Thanks a lot, Wolfgang. It has been very interesting, very complete overview of the situation. Is there any question, comments? Yes, there is Alvaro that wants to make a question. Please, Alvaro, go ahead.
Yes, good afternoon or good morning for you.
Yep.
Well, thanks for this very clear talk. And I have a question, or more a worry than a question. And that is about the concept of pool. It looks a little bit propagandistic to me, since when you employ, so to speak, the look elsewhere effect, which is something that is absolutely unavoidable, there is no significant statistics without looking everywhere, it reduces the significance a lot. So why introduce pool, which is, in my external opinion, a rather untenable concept? That's a statement. Now I have a question. When these people, Lanciarini et al., look at global significances, do they, in those plots where you have something that depends on Q squared, look at every point in Q squared, or only some of them, or only the ensemble? How does that work in practice?
So if I remember correctly, they take into account all Q square bins. So the data is presented in bins of Q square, and one just takes into account all of the bins that have been measured.
Independently.
Independently, yes. But
Okay,
taking into account, of course, the correlations among the measurements, etc., which is also provided by the experimental collaborations.
Okay, thank you.
And concerning the comment about pulls, I mean, to some extent, I do agree, and that's why I did put this this comment down here that there is this studies of global significance. The reason why the pull is typically quoted, because it's a very simple thing that one can quote, and it doesn't need too much work to give that result. And then one, of course, one has to be careful in how to interpret that value.
Yeah, but since you call it sigma, which is the same you call a standard deviation, which is
Okay.
analyzed in a standard manner, it should be called sigma prime or tau instead of sigma, something else.
Okay, fair enough, fair enough.
Is there any other question or comment? In the meantime, I can do one. So if you do the typical question, which is your favorite model, you already answered that you prefer the one with the Z prime.
Mm-hmm.
But there are others that reply that their favorite models are with leptoquarks.
Yeah.
What is the disadvantages that we can see in leptoquarks model from this point of view?
It depends. So there are. So I think that the big strengths of leptoquark models is that they can explain not only all those anomalies that I've shown here, but also the anomalies in the charged current decays. So if you go back to the very beginning here, so what I've shown were these B2S LL decays, and the Z prime can explain all those red anomalies, but the Z prime cannot do the RD and RD star, and leptoquarks can also do RD and RD star on top. So that is the big advantage of leptoquarks. Now the problem, or I don't know if the problem, but the one issue with leptoquarks is that if you want to explain also RD and RD stars, these leptoquarks, they tend to be pretty light, and they can be at most a few TeV. And then the question arises, why haven't we seen those leptoquarks at the LHC yet? And in fact, there are strong constraints already from direct searches for leptoquarks and also from measurements of di-tau spectra, for example, which put very strong constraints on these types of leptoquark models. So it's so if the LHC continues not to see any of those leptoquark effects, it's becoming more and more difficult to make those models work.
I see. Yes, there's Belen with hands. So please.
Yeah, for the most there in the screen, no, those that depend less on hadronic effects like the RK star, etc., the more solid. You're comparing still muons with electrons. As you are following the subject, do you know what the experimentalists are doing right now to be sure of the experimental uncertainties coming from comparing electron with muons, how you separate what is the low being from higher ones, etc.?
Yeah, I can say a bit about that. So the way the measurement is done on the experimental side is that they are using double ratios. So they're actually not measuring, let's say, B to K mu mu or B to K EE, but they add in another ratio, which is B to shape psi E and B to shape psi mu. Shape psi, which then the shape psi goes to mu mu and shape psi goes to EE. And so that is supposed to reduce the experimental uncertainties quite a bit, because now they don't need to understand absolute efficiencies for electrons and muons, but only relative between those different decay modes. And they do test that. For example, they also use the same method to test lepton flavor universality of the psi prime, for example.
Okay, I knew the J of psi. Now you say they use the psi prime too?
Yes,
yeah.
So they basically use the psi to measure the psi prime and to confirm lepton flavor universality in psi prime, and they find that this is in agreement at the percent level with lepton flavor universality. So they have all of that cross checks, and they all work out. So it's if it is an experimental effect, it's a very, very strange experimental effect that for some reason only shows up in this rare BDKs, B2K mu mu and B2K star mu mu and EE, but not in the other decays that they're testing that.
Yeah, it also depends how you pair the beams. But okay, thank you.
Any other question or comment? So it seems not. We are running pretty late with the time. So if there are no other questions or comment, let's thank again Wolfgang. Thanks a lot for this nice review, and hope to see you soon personally.
Yes, I also hope so.
So thanks again, and greetings to Stefania.
Thank you. Thank you.
Bye. Thank you.
Bye-bye.